Hey everyone, welcome back, or if you're just joining us, welcome to KSSP Podcast. I'm Spencer.
Yeah, I'm Katie. Today we're going to go over the life cycle of stars, just a little overview. So we can start with this video, GCSE Physics, the lifestyles of stars, how they're formed, and some other stuff.
Yes, so we'll get started.
In today's video, we're going to look at the life cycle of stars. It all starts with a big cloud of dust and gas, which we call a nebula. Over time, the attractive force of gravity pulls the dust and gas together to form a structure called a protostar. And as more and more particles collide and join the protostar, it gets bigger and bigger. And so its force of gravity gets even stronger, which allows it to attract ever more dust and gas. The gravity also squeezes the protostar itself, making it more and more dense. This means that the particles inside it collide with each other more often, which in turn raises the temperature of the protostar.
Interesting.
Then, when the temperature and pressure get high enough, hydrogen nuclei start to fuse together to form helium nuclei, in a process called nuclear fusion. This gives out huge amounts of energy, which keeps the core of the star hot. And it's at this point that we call it an actual star, or more precisely, a main sequence star.
Okay.
So, gravity. Again.
Oh, yeah, it always comes down to gravity. If you're ever dealing
Why?
with matter that has mass, why? Because that's just the way it goes. That's just the way the universe is coded.
Because it's the objects that have the gravity.
Right.
So the gas and dust has gravity.
Yes.
And then the
Everything is
gravity of each other is pulling it together.
Yeah, it's like it sounds like it's squishing it at the center, making the particles collide.
And what keeps that from happening to us in a planet, Earth, the star?
I
Like,
think
why
because we're
don't we
made
get
of
pulled
more
together?
stable elements, like carbon.
Oh. Okay. I mean, I guess I get...
That would be my guess, at least. I mean, I'm not a scientist, but...
So, like, the universe starts as gas and dust and then forms stars and planetary bodies that then have mass and gravity
Yes.
enough to where it's the exact amount needed to keep each other at the safe distance?
What do you mean by that, I guess?
So, like, the Earth and Sun have just the right amount of mass and gravity to keep each other from being pulled one way or the other.
Yeah, and also the distance, too. Don't forget the distance. Because if we were like... I think the distance has to do with it, too.
Yeah, but what created the distance? Did the Earth just magically form at that particular distance? Just we were
Well,
lucky?
probably the same way, this similar way to how stars form, just from, the Big Bang and matter being expelled everywhere, making a big old mess. And then, like, eventually the gravity of all these, little particles and all these atoms, like, will come together and form different types of matter, I guess, is the best way I would explain it. I'm really terrible at explaining this, but...
Well, no, I guess, like, I think, I get what you're saying. I don't know if that answers, like, my...
Yeah.
But I don't know if there's an answer to my question, because I don't think they know.
I was saying there might not be an answer. I don't know.
Because really, how would we, like, they're, like... Because basically my question is, why are we at the perfect distance? Why are the planets at the perfect distance? Why did they form at that particular distance?
Oh, I
Just luck?
assume that other matter had also formed, but because it would be like maybe an incorrect distance from the sun, let's say, like it would either get sucked in or propelled out.
So you think, okay. So in your theory, then there's been, like, if the sun is like, we're just gonna say the sun is in the middle, and
Yeah,
then there maybe were tiny little forming around the sun, but then what's the first planet from the sun?
Mercury.
Mercury also was forming.
Yeah,
I guess, like, why were all these forming? Like, what prevented them from all getting pulled into the sun?
I mean, I think that's just the way that the gravity works. I don't know if there's an answer really to that question. There might be. There could be.
I mean, I guess there doesn't have to be an answer. It's just that's what I'm thinking. Like, why? I just,
Yeah. Oh, yeah, that makes sense.
because then it formed a perfect. I mean, not maybe not perfect in some people's eyes, but just it formed a perfect, what we consider perfect universe because it allows us to live. You know,
Yeah.
like if it would have been
Maybe
any
not
different,
the
then
universe.
humans probably wouldn't exist. But
Yeah, true.
it's just interesting.
Yeah.
It's comes down to luck, I guess. Was what I would is what I
Yeah, that's
think. It's
true.
just luck. But okay, should we keep playing?
Yeah, let's keep going here.
Okay, see what else.
While it's a main sequence star, the outward pressure caused by all of that energy that's being released by nuclear fusion is perfectly balanced by the inward pressure caused by gravity. This allows for a long, stable period that can last for billions of years. And it's this stage that our sun is currently in. At some point, though, the star will start to run out of hydrogen, which, remember, is effectively its fuel. You don't need to worry about the details, but basically, this means that the star won't be able to do any more nuclear fusion. And so the inward pressure of gravity
Yeah.
takes over and contracts the star into a small ball until it's so hot and dense that nuclear fusion can start up again, which will cause it to expand again. This time, though, instead of just forming helium, the nuclear fusion will form heavier elements, including all the elements up to iron on the periodic table.
But pause. For a second. Has this happened to our sun yet? Do you think?
No, I don't. What do you mean?
Like this part. Like have we
I
gotten to
don't.
the part where it condensed and then grew back, or is that still coming? Is that still coming up?
Oh, I think it's still coming, isn't it? Like if they were,
I'm
because
not sure what
in
point in
this,
yeah. Because the
um,
sun is 4.6 billion years old, and it's about halfway through its life cycle.
in our theories,
Yeah,
based off of our
according to theory.
theories,
Yeah.
um, well, because in this stage, doesn't it? Our sun still has hydrogen, though, doesn't it? Like with the measurements they've taken,
Oh, that's true. Yeah.
and I think in this one it ran
But
out
I
of
think it also
hydrogen.
makes heavier elements too, though.
Our sun does.
From what I was reading, yeah.
I don't know then. I
Maybe
guess.
we've done this. I don't know. Because I imagine, like, the inward pressure, like, if there wasn't any way, like, if it didn't keep making fusion as it got smaller, like, isn't that how, like, a black hole would form at the end of the life? Is because it's not able to make any more fusion, so it would, like, the gravity collapses on itself, basically.
Like it's not putting any outward, like exerting the fusion force.
Exactly. That would be my theory at this point, but maybe the video will prove me wrong.
We'll keep going and see what they say.
For sure.
Exactly how much the star expands depends on how big the initial star was. If it was a small to medium star, like our sun, then it will form a red giant. But if it was a really big star, then it would form a red supergiant. Each of these two types complete the rest of their life cycles in different ways. So we're going to take a look at the red giant first, and then we'll come back to the red supergiant.
Okay.
After a relatively short time, the red giant becomes unstable and expels its outer layers of dust and gas. This leaves behind a hot, dense, solid core, which doesn't do any nuclear fusion. We call this a white dwarf because it gives off lots of light, so it appears white, and is relatively small. Over time, the white dwarf gets cooler and darker as it emits all of its energy, until finally it transitions to a black dwarf because it no longer has enough energy to emit light, and so appears dark.
Interesting.
Now, if we whisk back to the two options for our main sequence star, the other possibility for the really big stars was to turn into a red supergiant. So let's now look at these. Red supergiants actually start to shine brightly again as they undergo even more nuclear fusion.
Oh, wow.
After passing through several cycles of expansion and contraction, though, they eventually explode in something called a supernova, which forms elements even heavier than iron that get ejected all across the universe. What happens next, again, depends on how big the star was. If it was just very big, then it will condense into a very dense core called a neutron star. However, if the star was absolutely massive, then it might collapse in on itself and become a black hole.
Yep.
The reason we call them black holes is because they're so dense that their gravity is able to pull in any light that passes nearby, which means that they literally appear as empty spaces, or tiny holes in the universe where no light is ever emitted. So to quickly recap everything, stars initially form from clouds of dust and gas that slowly come together under the attractive force of gravity to form a protostar. When the pressure and temperature get high enough, nuclear fusion takes off, and we transition to a main sequence star. After a long time, often billions of years, the star exhausts its hydrogen supplies and becomes either a red giant, if it's a small to medium size, or a red supergiant if it's a big star. The red giants throw off their outer layers to reveal a hot, dense core that we call a white dwarf, which then cools to become a black dwarf. Meanwhile, the red supergiant explodes in a supernova, ejecting heavy elements across the universe. And it then condenses into a neutron star if it was only pretty big, or into a black hole if it was truly massive.
Pause it for a sec. So, I guess we're almost done with it, but is the supernova, is that an implosion or an explosion? I don't know if you mentioned that. If I missed that.
I think
I can look it up too.
I want to say explosion, but I don't know if he did mention that.
Oh, okay, it is an explosion.
And then for like our knowledge, everything that we our knowledge on fusion that we use on Earth or attempt to use for energy sources, did we learn all that from astrology? Or did some of it
Astronomy, you mean?
yeah,
I would say
astronomy.
astrology is different, yeah. But I would think so. I don't know for sure, but I would think we learned that all from learning about the sun.
Interesting. So we're just trying to copy what the sun does.
I guess. In a sense.
That's interesting. Yeah, I don't know. It's just interesting that stars are like their own reactors, kind of.
Yeah.
Like they have their own internal reactors, and
Yes.
it just happened again, like it just
Yeah.
because, just
Yeah.
the fate of the universe dictated it, you know?
Yes.
Okay.
That's everything for today, though. So if you enjoyed it, then please do give us a like and subscribe, and we'll see you again soon.
All right, cool.
Sweet.
So, all right, we're going to talk about the life cycle of a star. And I just want to show an image really quick that I think looks really pretty from this article. That's this life cycle of a star right here. So there's a stellar nebula, right? And then the average star turns into the red giant, and a red giant turns into the planetary nebula, which it looks like it contains the white dwarf. I'm not sure if that's the same thing in the middle of the planetary nebula, but we can learn.
Yeah.
And then if it's a massive star, it'll be a red supergiant, turn to a supernova, and then either a neutron star or a black hole, or both potentially. So the lifetime of a star depends very much on its size. Massive stars use up their fuel quickly. This means they only last a few 100,000 years. Smaller stars use up fuel more slowly, so they will shine for several billion years. So eventually the hydrogen which powers the nuclear reactions inside the star begin to run out, and they enter the final phase of their lifetime. So they expand, cool, and change color to become a red giant. And then what happens next depends on the size of the star. So the smaller star, like the sun, will gradually cool down and stop glowing. During these changes, it will go through the planetary nebula phase and the white dwarf phase. After many thousands of millions of years, it will stop glowing and become a black dwarf. A massive star experiences a much more energetic and violent end. It explodes as a supernova, and this scatters materials from inside the star across space. And the material can collect in nebulae and form the next generation of stars. And then after the dust clears, a very dense neutron star is left behind. These spin rapidly and give off streams of radiation known as pulsars. And if the star is especially massive, when it explodes, it forms a black hole. So that's that article. And then I've also got some fun facts about stars and the life cycle of the stars and the sun. So let's see. Every star you can see is much bigger and glows brighter than our sun. The sun looks the brightest and biggest because it's the closest star to us. You can't see 1 million stars in the sky at one time. You cannot. The color red doesn't mean hot in space, it means cool. So if you look at a red star, that means the star is cool, not hot. If the star is blue, that means it is hot. And stars have black bodies, and there are no green stars. That means not many stars look green, and if they do, it's because of your telescope. Our sun is actually a dwarf star. Stars don't actually twinkle. You can see at least 20 quadrillion miles into space. Wow. And then black holes don't suck. They just use gravity to pull stars and space junk into them. The sun is the star that provides the conditions to live on Earth. So those are some fun facts about stars. I think you had a couple more.
Yeah, I have a couple here that I found when I was looking things up. So I found that the stars in a particular cluster have a common birthday. They formed from a gas cloud all at the same time. Some stars are born having high luminosity and high temperature, while others are born having low luminosity and low temperature. And then the centers of stars, as we learned, are hot enough to create a nuclear furnace. All electrons are stripped entirely from their atoms, leaving their nuclei bare. And then just how long like a massive blue star can live for perhaps 10 million years. So it's just interesting how, like, the length of time that stars
I just think the
live
blue
for.
stars are interesting to me.
Blue stars?
Yeah. It just sounds so pretty.
Yeah, I guess I don't know much of the difference between the different colored stars, but
And I'll go over that later too.
oh, okay, okay. But yeah, stars are just they're. I think, yeah, they all have their own unique beauty, right?
They're so big. Like you think about
Well,
how big
yeah,
they are. Like it's crazy. And our sun is way bigger than the Earth, and it's like not even the close. It's a dwarf star. That said, it's a tiny little star.
yeah. So then they can be bigger.
Yeah, exactly. It can be really, really, really big. Yeah, we'll see that
Yeah,
in another
but
video.
now that we've just kind of covered the brief overview of the star's basic life cycle, join us in the next video as we go more in depth on what a stellar nebula is. And you can always leave a comment letting us know if there's any topics you want us to talk about in future episodes as well.
Yeah, you can find us on Facebook, YouTube, Instagram, Twitter, and TikTok, and occasionally we do some Twitch live streams.
And don't forget to like, follow, or subscribe and turn on notifications so that you know when we do. Otherwise, we will see you all in the next video.